was a kid growing up and learning about baseball, I could never understand why the catcher on the team, who was like had all the defensive skills, could never hit the home runs, you know. It wasn't until I got older and had my first stats course that you realize that sometimes abilities in different domains aren't correlated. You have somebody who's outstanding in one area.
Should I give it to him?
You know, it's very, very unlikely to find people that are really skilled in more than one area. And I think by that sort of analogy, Jack McDowell, our next speaker, is a very, very special person. He's not only an outstanding clinician, but he's also an outstanding researcher. And that may be even more unusual than being a defensive catcher who can lead the league in homers. Jack received his bachelor's from Yale, and from there went to State University of New York, Stony Brook, where he completed his PhD with Howie Racklin in 1979. And the title of his PhD was Some Contributions to the Mathematical Description of Behavior. So there's a clinical PhD for you. Jack went straight to Emory University in Georgia, where he rapidly rose through the ranks and is currently full professor of psychology. And he's been a great mentor for many students at Emory. Some of his best-known PhD students include John Wickstead at UC San Diego and Jesse Dollery at the University of Florida. And Jack, I remember when I was just a beginning graduate student, and I think it was at an APA meeting. I just went into a talk that Jack was giving, and it was on the applications of the matching law to self-injurious behavior, basically doing behavior modification. And I was just blown away by the clarity of his talk, and so impressed by being able to take a quantitative theory from the basic research domain and show how it could be clinically relevant. And I still remember that talk, and Jack is, so we really have something to look forward to here today. I guess there's not too much more to say, except that I saw the abstract of Jack's presentation. I'm really, really curious to see what he has to say, and I'm sure we'll learn a lot. And thank you very much, Jack.
Thanks, Randy. Thank you. Thanks for that nice introduction. The reason that abstract was incomprehensible or was puzzling was because I hadn't quite planned what I was going to say. So that's why I now have a colon here and additional information about what I'm going to talk about today. I will say I have another great graduate student who has just finished his PhD, Dr. Paul Soto. I didn't want to leave him out of the group of individuals. I'm going to talk about a particular topic. Do I do N? Yeah, I got it. A particular topic in this larger area of fitting equations to data. There are a lot of reasons that you might want to do this. Here's perhaps the most elementary. You just want to describe a set of data. You hear about cubic splines. You've got a bunch of data, and you think you're going to be quantitative, and you're going to draw some function through there, and sometimes it's fun to do. It's not particularly useful, except perhaps to do some interpolation between data points. Another thing that objective when you're fitting equations to data is to search for a mathematical relationship among variables or between variables. This is something that we see a fair amount of in behavior analysis, and it's a good way to get an inductive kind of mathematical theory. And then there's a third reason for fitting equations to data that I'm going to talk most about today, and that's testing a mathematical theory. And this is a theory that could be developed by induction, like in number 2 there, or a theory that's been developed formally. So once you have a theory, the question is, the thing I'm going to talk about today is how do you evaluate that theory? This is going to be a case study, so I'm going to talk about a particular theory, and that theory is going to be matching theory. However, the things that I'm going to talk about today are, I believe, generally applicable to testing mathematical theories in behavior analysis. Now, is that scary? Don't look away. find your anxiety dissipating? I've laid out here two kinds of ways of looking at matching theory. On the left, you see what I'm going to call classic matching theory, and on the right, what I'm going to call modern matching theory. This isn't really that scary because some of these things you've seen a lot of. You've seen this a lot of. You've seen this a lot. And some of these other equations you've seen here and there. Other of these equations you haven't seen in many places. But let me start with classic matching theory, which is matching theory circa about 1970. Actually, both of these theories are developed from the top down. So the top two equations here on these two sides were really developed inductively using the number 2 rationale from the last slide. They were developed inductively. But from there on, the derivation of these equations is a formal algebraic exercise based on some assumptions. And those are the assumptions that all behavior is choice behavior. You remember this from Dick Herrnstein's famous 1970 paper. All behavior is choice behavior that's allocated among available alternatives, and there's a constant amount of behavior that gets allocated among those alternatives. That produces this equation, and then this single alternative equation can be applied to the two sides of a concurrent schedule like this, and that's what these 4 equations of classic matching theory are. So these two are just applications of the single alternative equation to the two sides of a concurrent schedule. If you divide these two equations by each other, you get that one back again. This side works exactly the same way. That's the inductive form of power function matching that we know about today. And the very same theory, these are all discussed, by the way. I'm not going to go into this in detail. These are all discussed in this paper. So these equations have been around for a long time, although we don't really talk about them. We don't talk about them hardly at all. Sometimes this one, but never these down here. But the derivation is exactly identical on the two sides. So it's the same rationale, and the same assumptions are used, and then you just do the algebra. That's what happens. And as a consequence, you get a single alternative equation. This is the equation that comes from power function matching, describing the relationship between response rate and reinforcement rate. And these are the equations that describe two sides of a concurrent schedule. If you divide this by this, believe it or not, you'll get this equation back again. And interestingly, in what I'm calling modern matching theory, there's a second matching equation, which is discussed in this article here. That's the second matching equation. I'm not going to go into all these details because I want to really focus on how you evaluate these theories today. It's probably better to call this a special case of modern matching theory, and the little arrows tell you which are the equations, of course, that correspond to each other. The thing you see immediately here is that there are exponents and bias parameters in all the equations on the right. If those exponents and bias parameters are all equal to 1, you get all the equations on the left again. And so the left is really a special case of the general equations on the right. If you do that, make all the exponents and bias parameters 1 here, you get this equation back again. Okay, so that's the theory that I'm going to talk about. I'm going to skip this. Those are the two equations that we're most familiar with, one from column A and one from column B, which is a little bit logically peculiar, I think. Here's what I'm going to do. If I have a set of concurrent scheduled data, what I really ought to do, I want to assert, is fit all 3 of these equations, the ratio form of matching and the two single alternative equations to each side of the concurrent schedule. Of course, there's no fitting involved here because there are no parameters to estimate. So to start with, I'm going to focus on these 2 equations and fitting these 2 equations simultaneously to a set of concurrent scheduled data. So I have 2 sources of variance. I have the response rates on side 1, and I have the response rates on side 2. And what I want to do is fit these 2 equations simultaneously with a shared K and a shared R sub B in order to test this theory. Because according to this theory, the K and the R sub B have to be the same on both sides. Otherwise, if I divide this by this, I don't get this equation back again. So that's what I want to do. I want to fit these 2 equations simultaneously to 2 sources of variance. The problem here is, what do I minimize when I do this? When I do least squares regression, you'll remember from what you know about least squares regression, the way you estimate parameters is by minimizing the residual sum of squares. You take each residual, square it, and sum it, and you want to find parameters that give you the smallest, that make that sum the smallest. So typically what you do is minimize the residual sum of squares. That's the notation that I'll be using. But if I have two sources of variance, not just one, I have two, the response rates on each side of a concurrent schedule, what do I minimize when I want to do a fit simultaneously with shared parameters? Well, one thing you might think to do is to just add the separate sources of variance. Here I'm adding more than two, but for our example here, I would add the residual sum of squares on one side and the residual sum of squares on the other side, adjust the k and the r sub b parameters until that sum is a minimum, and say that's the best fit that I have. Well, that's a good idea, but in fact it doesn't work, and here's why it doesn't work. When you do this kind of calculation, you're going to be using some algorithm, some optimality algorithm. Mathematica has one. You probably don't use that, although it's an interesting one to look at. SPSS has one, has an algorithm that will minimize a quantity by adjusting parameter values. There are freestanding programs like at graphpad.com. You can find some. There are many, many such programs. Perhaps the most accessible one is a program that comes with Microsoft Excel called Solver. And all you have to do is go to your solver and click on Help and type in Solver, and it's not loaded by default. You have to. It's on your CD though, and you can see how to add that in, and it's widely available and an excellent algorithm. But when you use an algorithm like that, here's what happens. Sometimes, not always, sometimes this works, but you can't rely on it, because sometimes what happens is these algorithms make one residual sum of squares really, really small and leave the other one kind of big, such that the sum is small, but you don't have what you want, which are really the best fits of the equations to the two sources of variance. So you think, well, maybe you should do something like this, kind of normalize it. You think of this is the total sum of squares. That's related to all the variability that there is in the data. This is the variability that's left over after the equation accounts for whatever it wants to account for. You think, well, this might sort of normalize things, but it doesn't work because it has the same problem. Sometimes it works, but you can't rely on it. So it turns out that this is the quantity that does an excellent job when you're trying to fit to multiple sources of variance. You take each residual sum of squares and divide it by its corresponding total sum of squares. So in normal circumstances, this quantity will vary between 0 and 1. So all the terms in this sum are kind of normalized. And if you minimize the whole sum, you'll find that you get really very good fits. And we'll see some examples of that today. So that's the first thing that we want to remember today, is that this is the quantity to minimize when you're fitting to multiple sources of variance. Now, the example that I'm going to use is 5 concurrent VI-VI schedules. There's 7 cents per reinforcer on each side. It's data from a human subject. And I'm going to fit these two equations to each side simultaneously of the concurrent schedule. Here's the quantity I'm going to minimize. There is the sum of these ratios. This is related to the leftover unexplained variance. So I'm minimizing the sum of these leftover unexplained variances. Now, just so that we get this straight, when we do this kind of curve fitting, how do the parameter estimates fit into this quantity that's being minimized? In other words, when we minimize this, how come that's changing the k and the r sub b in these equations? Well, here's the way to think of it. We're talking about residuals here, so the r is the observed response rate, and r prime is the response rate calculated from one of these equations. Well, in order to calculate it from one of these equations, you need a k and an r sub b. So you have to start this fitting with a particular k and an r sub b, let's say a k of 100 and an r sub b of 25, and that gives me a calculated r, that's the r prime. I subtract that r prime from the r, square it, and sum it, and that's how I get my residuals. And I see how large this quantity is, and if it's and then I try a different k and an r sub b, and so on, in order to minimize that residual sum of squares. So the parameters enter into this quantity because they're used to calculate the part of the residual, which appears in the numerators here. So keeping this in mind, your optimality algorithm is going to adjust the k and the r sub b parameters to minimize whatever quantity you want to minimize, and in this case you'll be minimizing this one. There are a lot of different algorithms out there, and if you look at this literature, you'll see these names. All of them are good. This includes this one. You don't see this one all by itself anymore. But modern programs do this pretty well, so you can pretty much pick and choose whichever one you want. This is an interesting topic, and we could talk about it, but I'm not going to talk about it today, how these algorithms work, how they actually search in a kind of reasonable way a parameter space to find the best parameters without doing it by brute force. But the solver in Microsoft Excel uses this last algorithm down here. Okay. So let's look at our example. I have some data, and I'm going to calculate this residual, this quantity here, and I'm going to use my algorithm to find the best fitting k in the R sub b, and there they are. There's the best fitting k in an R sub b for the particular data I'm talking about. Here the percent variance is accounted for. For side 1, I have about 99% of the variance accounted for, and for side 2, 99% of the variance accounted for. When you do these fits, it's nice to have, I think, an ensemble percent variance accounted for. I like to call these ensemble fits, where I have one number that tells me how good all the fits are, and that's calculated from one of the other equations on that on a previous slide, where you first sum the residual sum of squares and then divide by all the separate total sums of squares, and that gives you the error term to use to calculate the ensemble. So what we see here is we have really a very good fit. It looks like the data for this particular subject are well described by this theory, and that we could say that the data are consistent with this theory. Here's a plot. Is that all wavy? Oh no, it's just my perspective. Here's a plot of the best fitting surface. This is the response rate on side 1 or side 2. This is the reinforcement rate on that same side. This is the reinforcement rate on the other side. These, of course, are surfaces. These equations express response rate as a function of two variables, reinforcement rate on the same side and reinforcement rate on the opposite side. So they're surfaces like this. Here you see the little hyperbolic cross-section that you would expect to see. And if you take a particular reinforcement rate on side 1 and ask what happens to response rate on side 1 as you increase reinforcement rate on side 2, you can see the little decline, of course, that you know happens when you increase reinforcement rate on side 2. So that's a plot of the best fitting. That's a plot of the best fitting equation here. Now, we think that we have a good test of this theory here, but in fact we don't, because we need to look at the residuals. The residuals are what's left over. We account for a lot of variance, but the leftover variance, is it systematic or is it random? This is something we don't do all the time in behavior analysis, but we should do a lot more often, is to look at these residuals, because in order for this theory to be correct, the residuals need to vary randomly around this surface, not systematically. And here's an example of that. Here's some data that I have calculated, the blue diamonds there, and I fitted a function, the magenta function, through there, and it accounts for 98% of the variance in the blue diamonds. That's a lot. A lot of variance is accounted for, but obviously you can see that that function is not the correct description of those data. There's systematic variability. The data overshoot here, they undershoot here, and they overshoot here. So we'd have to conclude that whatever this theory is, it doesn't describe these data, even though a lot of variance is accounted for. This is why we have to look at residuals. Well, you can look at residuals this way, and it's a good way to do it in an actual plot. But a more common way to look at residuals is to plot the residual, which is the little vertical distance between the data point and the function, plot the residual as a function of the predicted response rate. So I've predicted response rate right here, and I'm plotting the residual at each of the predicted response rates here. Now, in fact, it's not the actual residual, it's the standardized residual, which is probably one of the most popular ways to look at residuals, so I'm doing it this way, where I've expressed the residual as a z-score in terms of its mean and standard deviation based on n. And so here's a plot of those residuals. This is a good example of something you absolutely never want to see in a residual plot, a pattern like this. And there's the overshoot right here, there's the undershoot right here, and there's the overshoot right there. Now, I fitted a straight line to this because these, of course, there's no error in the fabricated data that I'm showing you here. But if there were a little Gaussian error, as there would be in the case of an actual subject, these residuals would be bouncing around and so on. You may not be able to detect the actual form of the deviation, but you would see a pattern. And in this case, you would see a declining linear trend like this. By the way, a cubic polynomial describes these data very well. And that's an example of the first use of equation fitting, which doesn't really tell you that much. It's just something to say about it. It looks like a cubic polynomial. Well, let me tell you something as an aside. These data points come from the modern form of the single alternative equation with an exponent of about 0.65 or 0.7, I think. And the plot and the fit is a fit of the classic, what I'm calling the classic form, the form we typically think about. And what I want to kind of hint to you, although this is an aside, is that it may be the case that this equation actually isn't correct. And yet we have tons of data that show it accounts for a lot of variance. And it may be that there are little deviations. If this equation is correct instead of this one, then there may be a little bit of systematic deviation from this function form. But we don't often look at that. It would be interesting for us to look at that, I think. OK, that's an aside. Let's go back to our example. We need to look at residuals here. We have a lot of variance accounted for. We need to look at residuals. They don't look so good. In blue, I've plotted the residuals for one side. In magenta, the residuals for the other side. Both show a declining trend here. The correlation coefficient is negative 0.76. So there's a pattern in the residuals. So I'm going to have to conclude that even though a lot of variance is accounted for, the systematic residuals indicate that these equations do not, in fact, accurately describe these data. Well, let's relax the theory a little bit. I'm just sort of doing this. Oh, no. First, I want to tell you that this is part of a larger experiment. There were, in fact, 5 magnitude pairs in this experiment, not just 2. Here's what the whole experiment looks like. What we've been looking at is what I'm calling condition C here, where there's 7 cents on each side. In fact, there were these other conditions where the magnitude pairs varied. On one side, it was always 7 cents. But on the other side, it could be as much as 20 cents or as much as a quarter of a cent. I didn't do this correctly. It's a quarter of a cent, not what I've indicated here. It's not this small. It's small, but it's not this small. And here's the equal magnitude condition. So I've showed you a fit to just these 2 conditions. But in fact, if we want to evaluate the classic matching theory, what we ought to do is fit the 2 equations to all 10 sources of variance at the same time with the same k and the same r sub b, shared k and an r sub b. It's not a problem, actually. We can do that. Here are the 2 equations that we want to fit. Now what we're going to do is minimize a different sum. The idea is still the same, but now instead of minimizing a sum of 2 of these, we're minimizing a sum of 10 of them. So for each magnitude pair, I have a quantity that describes the leftover variance on each side, and so I have 10 sources of variance instead of 2. And I just tell my program to minimize this quantity. You see that the k and r sub b fit into this the same way because the k and r sub b are used to calculate every single residual sum of squares here. You'll find that your optimality algorithms will handle this very nicely. We'll be able to do this very well. So we did that, and here's the result. Here's the old result for just condition C, the equal magnitude condition. But for all conditions, this is just one subject. For all conditions, the k and r sub b aren't very different from each other, and I get pretty good fits here. You can look down here. This is for each side of each condition. This is for both sides of each condition. This is for one side over all conditions, side 2 over all conditions. And let's look at this one, because this is for the whole ensemble. 96% of the variance accounted for. We'd say that's pretty good. That's a pretty good fit. But again, we need to look at the residuals. If we look at the residuals, I'm identifying this subject now. If we look at the residuals, we find that there is a pattern still, and so we've got a problem here. If I put this here to show you what the data look like. I've twisted this surface all around. This is the best fitting surface. This is still the response rate on side 1 or side 2. This is reinforcement rate on that side. This is reinforcement rate on the other side. And what you can see here is that here are data points that are lying on top of the surface. That's right here. Here are data points that are doing what they're supposed to be doing. They're sort of bouncing around the surface. And here are data points which you might not be able to see because of the contrast in this image. Data points that are hanging below the surface. That's these data points right here. So that shows that the residuals aren't looking too good here. If you pool the residuals for all the subjects, which is an interesting thing to do, although you have to be cautious about doing that. But because you're using the standardized residuals, you can do it. There were actually 4 subjects in this experiment. They all showed this kind of deviation. They all produced good fits. I haven't shown you those fits. But if you pool for all the subjects, you see that you get this deviation. Well, so we're going to have to conclude that these equations do not, in fact, describe are not. The theory is not correct if the residuals are non-random like that. Are you with me? If you want to be. Let's try a variation of the theory. Let's relax the theory a little bit. You can actually, there's a form of this theory also discussed in this paper if you're interested. There's a form of this theory, the classical theory, where you can have different k's for each magnitude pair. So as before I was sharing 2 parameters for all 10 sources of variance, now I'm going to have a separate k for each magnitude pair and a single R sub e. Why that's a reasonable variation of this theory I'm not going to go into, but it'll help illustrate this method and how we can test these kinds of variations. So now I'm going to fit 6 parameters, not 2. I'm going to fit them to the same source of variance, I'm going to use the same quantity to minimize because I have the same 10 sources of variance, but now I'm going to simultaneously estimate 5 k's, 1 per condition, and 1 R sub e. Is that a problem? No, it's not a problem, because now instead of using the same k to calculate all of these, I'll use 1 k to calculate these. That k has to, according to this theory, has to be the same on both sides of the concurrent schedule. 1 k to calculate these residual sum of squares, a different k here, and a different k for every condition, and then a single R sub e. And in fact, you'll find that your optimality algorithms will handle this perfectly. You have to identify which parameters you want to adjust, what quantity you want to minimize, and you'll find that it works very well. So let's see what happens when we do this. We've relaxed the theory, and now we're accounting for still about 96% of the variance, even though we have 6 parameters instead of 2. Now, one of the maxims of fitting equations to data is that if you have more parameters, you account for more variance. In these ensemble fits, that's not necessarily true. Here we have more parameters, but we account for the same amount of variance. The question we want to know is, does this help our residuals at all? And in fact, the answer is it doesn't help our residuals. That's our sort of illustrative subject. And there's, for all the subjects, we have the same pattern in the residuals. So even this relaxed version of the theory isn't working out too well. So we're going to have to we're going to have to refrain from asserting that these data are consistent with that theory. Well, the heck with the theory. Let's forget this theory completely and just ask, what about the form? Forget what the k's and R sub e's are supposed to be. Is it the case, can we say that response rate is a function of these 2 reinforcement rates in this particular form? Okay, so now we'll go wild and have a separate k and a separate R sub e for every single side of every single different concurrent schedule. I'm going to let them vary completely. I have 20 parameters now. I had 2, then I went to 6. Now I'm going to do 20 different parameters, a separate k and a separate R sub e for every side of the concurrent schedule. What am I minimizing? Same thing, because I have the same 10 sources of variance. But now I have a different k and an R sub e for each one of these quantities that appears here. Oh, by the way, let's look at this. I'll do P. You could fit each of these separately, of course, because there are no shared parameters. You could fit each one separately, just do this one, then just do this one, then just do this one. Or you could fit the whole ensemble this way. If you just fit this, of course, you just minimize this quantity. If you fit this, you just minimize this quantity. Or you could do the whole ensemble like we've been doing, even though there are no shared parameters, and you get the same answer. So that shows you that the method's working out pretty well. So I fitted it as a whole ensemble. So this is what we're fitting. And here's the result we get. 97% of the variance accounted for when we allow different parameters in every single side of the concurrent schedule. We've only added 1% variance by going from 2 parameters to 20. So all those parameters aren't helping us at all. Could it possibly help us with the residuals? No. The residuals still look bad. If you pool for all subjects, they still look bad. It's the same overshoot and undershoot problem. So how do we evaluate this theory? There is no way that these 2 equations, reinforcement rate, the 2 reinforcement sources of reinforcement and concurrent schedule, simply do not govern response rate in this form, at least for these data. There's no way that's the case. We know that that's not right for these data because that experiment is intended to produce bias, so that's not right. I'm going to just pass this by. I might make a comment on that later. Okay, so we're going to abandon now the classic theory for these data, and let's look at the modern. We're going to look at the modern theory. Now, although this looks a little frightening to you, I'm not going to go into a whole lot of detail about these equations. They're very interesting, and you can read about them in here. But just to orient you a little bit, here's what's happening in these equations. Every pair of reinforcement sources is being compared. The reinforcement source on the two sides of a concurrent schedule, that's one pairing. The reinforcement on side 1 with the background reinforcement that's required by the theory, that's the second pairing. And the reinforcement on side 2 of the concurrent schedule with the background reinforcement, that's the third pairing. Each of these pairings has a bias parameter and an exponent. So in these equations, there's a k and an r sub e, just like there was here. But now there are 3 bias parameters and 3 exponents. So instead of having, for the strictest implementation of the theory, just 2 parameters, now I have 3 exponents, that's 6, plus a k and an r sub e, that's 8 parameters. Now, I didn't make any of this up. This is if you don't like the looks of this is just a natural consequence of matching theory when you start with this equation instead of this one. So we're stuck with, say, well, we don't like all those parameters. We need to have something with fewer parameters. That's fine, but this is the consequence of matching theory. I've sort of indicated where the independent variables are here. I'm going to skip through that. There's the k and the r sub e. These are the 2 equations that describe the 2 sides of a concurrent schedule. There you see the k and the r sub e. There are the bias parameters. There's the bias parameter for the concurrent schedule itself, which is the same as this one. And the bias parameter for side 1 against background extraneous. There's the bias parameter for side 2 against extraneous. And there are the exponents. That's just to orient us. This is another thing that shows you it's not as complicated as it looks. There are only 3 terms in all of these equations. All those terms are the same. Those 2 terms are the same. Those 2 terms are the same. We can worry about that another time. So here we have our summary. In modern matching theory, we have 4 equations. We have 2 matching equations. And we have the 2 single alternative equations for the 2 sides of the concurrent schedule. And we have a k and an r sub e, and we have a bias parameter and exponent for every possible pair of reinforcement rates. And let's see what we're going to do next. Okay, here now, when you get to this kind of thing, you need to be more careful about how you test a theory. So now we're going to get to the more general case of testing a theory, which also applied to this classic theory testing that we did, but we didn't have to do some of these steps because they weren't so complicated. One thing that happens when you get an equation like this is that some of the parameters are not independent just because of their algebraic structure where they happen to be located, meaning you can't estimate them independently statistically. And in fact, that's the case here, and that's what I mean by identify parameters that cannot be estimated independently is what I mean. Because if you don't do that, this requires a little bit of skill and experience to be able to do this and some algebraic knowledge. But if you don't do it, it's not the end of the world. What you'll find when you do the fits is that you'll get parameters that assume wild values. And the next time you do the fit, they'll have different values. And that's a sure sign that you failed to identify composite parameters in your equation. So the first thing you have to do is identify the composite parameters. Well, in fact, the bias parameters that compare side 1 with background and side 2 with background cannot be independently estimated in these equations. And sub e cannot be independently estimated in these equations. So we need to combine those, and I've done that here into a composite parameter. I just exponentiated r sub e and pulled it out, and there's a composite parameter on this side and on this side. I'm just going to identify that as c sub 1e and c sub 2e. And so in principle, we have these 8 parameters. In practice, we're going to estimate 7 parameters. So what will we be estimating? We'll be estimating the k. We'll be estimating the bias parameter for the actual concurrent schedule, the exponent for the actual concurrent schedule, and all the other exponents, and these 2 composite parameters we'll be estimating. Okay, in order to test the theory. And what we want to find is that these equations account for a lot of the variance and have random residuals. That's what we're looking for here. Are you with me more or less? Okay. Now, step 2, we've got to figure out how we're implementing the theory when we're this complicated. Now look over here. These are the 4 equations that I'm going to fit. Before I was fitting 2, now I'm going to fit 4 equations at the same time, all 4, with 15 parameters for the ensemble. And I'm going to fit to now 20 sources of variance. because I have these individual sources of variance, but these ratios also constitute a source of variance. You could say this is the same source of variance, but we're going to treat them separately because we're estimating different parameters on the same source of variance. So I got 4 sources of variance. I've got 4 sources of variance per condition. So I have 20 sources of variance overall. I've got 4 equations, and I've got 15 parameters, and it seems like an impossible task. Your algorithm will do this very nicely, in fact, believe it or not. And I just put what the composite parameters look like here to remind you. So that's our task, to fit these 4 equations simultaneously with 15 parameters. How are we going to identify these parameters to be consistent with the theory? How are we going to let these parameters vary? Well, we're going to make k be the same in all conditions. That's what I mean. And x means there's a separate estimate of that parameter. So in all the different magnitude pairs, I'm going to have just 1 k, because I have to have a constant amount of behavior in matching theory. And because we don't really, the exponent is not really part of matching theory. The exponent is part of that inductive development of power function matching. And so what that exponent, how we should really deal with that exponent is a little bit iffy. So what I'm going to do is make that exponent be the same for all conditions. Each of the 3 exponents I'm going to make be the same for all 3 conditions. You could have 1 exponent overall, and in fact I've done it that way, and it gets the same answer as this. For the bias parameter for the 2 sides of a concurrent schedule, of course that has to be different in the different conditions, because this is an experiment that produces bias. So this bias parameter I'm going to let vary. And this C sub 1e parameter, look at it up here. The C sub 1e parameter has a B sub 1e bias parameter. Remember that I'm changing the magnitude on side 1 as I go down. I'm making it smaller and smaller and smaller. So I'm producing a bias whenever a bias between side 1 and side 2. It makes sense to think that I'm going to also produce a bias between side 1 and the background reinforcement. So I'm going to let, and because that appears in C sub 1e, I'm going to let C sub 1e be different for all of these conditions, because that seems to me to be a reasonable interpretation of this theory. C sub 2e, on the other hand, I've got R sub e, which ought to be constant, A sub 2e, which I'm making constant, and B sub 2e also ought to be constant because I'm not changing the magnitude on side 2, and I'm presuming the background extraneous magnitude doesn't change. And so I'm going to have a constant C sub 2e here. So these are the 15 parameters. 1k, 5 bias parameters, 5 of these parameters, and 3 exponents. Okay, so it looks a little confusing to you, but if you sort of just get the general gist of things, that will be good. What am I minimizing? Now I have a monster sum to minimize. You think this is all going to fall apart and not work, but in fact it works out great. Before I was just minimizing these 2 things for each condition, but now I'm adding this source of variance for this equation and this source of variance for this equation. So now I have 4 sources of variance for each condition, 5 conditions, that's the 20 sources of variance. This is the actual quantity that you'll tell your optimizing algorithm to minimize while it adjusts these 15 parameters. And of course, the 15 parameters figure into the calculation of these residual sums of squares, and that's how your thing will work. So here are the results for this one subject, age 59. It's all the same data. Now I'm accounting for 99% of the variance overall. I had at most 97. When I totally abandoned classic matching theory and let K and R sub E do whatever it wanted, wherever it wanted, I was accounting for 96% or 97% of the variance. Now, in what I think is a reasonably strict interpretation of modern matching theory, I'm accounting for 99% of the variance. That's a bit more. And I'm using 15 parameters, not 20 parameters. I had 20 parameters before and was accounting for 96%, 97% of the variance. Now I got 15. I'm accounting for 99% of the variance with different equations. Here's what the second step. So this is step 3. You got to look at the percent variance accounted for, of course. But now, in a case like this, you got to look at the parameter estimates and say, are they reasonable? Do they make sense given the theory? Well, I don't know what to say about these. Let's look at the exponents. They're all less than 1. Why are they different? I don't know, but they're not like 0.0003. They're not 15. They're all less than 1. They're in a range that's not too bad. And the exponent that's for the actual concurrent schedule, side 1 and side 2, is 0.7, which is about what you'd expect in a concurrent schedule. So that's what our ensemble fitting did for us. Let's look at the bias parameter. Perfect. It's behaving perfectly. Let's look at the bias parameter for condition C, where the magnitudes are equal on the 2 sides. It's about 1. When I've got 20 cents on side 1 and 7 cents on the other, I have a bias parameter of 1.2. When I have a quarter of a cent on side 1 and 7 cents on side 2, I have a bias parameter of 0.6. the bias parameters are behaving exactly as they should. Furthermore, let's look at this composite parameter. Because the magnitude is decreasing here on side 1 as you go down, the bias for side 1 should decrease as you go down, which it does. But when you compare the bias on the reinforcement on side 1 with the background, it should do the same thing. This bias parameter should be decreasing as you go down here when you're comparing side 1 with a presumably constant background. So because this is going down, I should see this go up. I should see my statistical estimate of this quantity go up, and sure enough, it goes up. It's a nice monotonic increase. So that parameter is behaving as one would expect. And I don't know what to say about this one. It's just a number. I guess we could try to look at it. But those are the main features. We've got reasonable exponents. The bias parameters are behaving exactly as they ought to. So our parameter estimates look good. That gives us confidence. And next, of course, we want to look at the residuals. Here are just plots to look at some of these surfaces. That's from condition A and condition E. These equations, that's the complicated equations with all the exponents and stuff in them. They don't produce weird-looking surfaces of any sort. They just add a little. I don't know what they do exactly, but they look pretty normal. And they allow us to account for more variance overall for the whole ensemble. Okay, let's look at the residuals here. Here are the residuals for age 59, the one subject. And sure enough, those residuals are looking good now. Looking pretty good. Correlation coefficient is 0.08. Here are the residuals pooled for all the subjects. Not bad. Looking much, much better. For comparison, here's what we had before. This is when we totally abandoned the theory and we let K and R sub E do whatever it wanted, and we were accounting for 97% of the variance, and we have this pattern in the residuals. So we conclude on the basis of this analysis that these equations, which are the ones we just looked at, are consistent with the data. The data are consistent with these two equations. And they, in fact, are consistent with these two. I didn't show you the data for this and look at the residuals for this, but they are consistent with these two equations. And since we're dealing with concurrent schedules, we're not talking about the single alternative form, but we can have a question mark about it. But I'm thinking that actually this form is the correct form, and this form actually is not correct. And it works so well for the reason I showed you in that previous slide. And in fact, logically, that makes sense because we get this equation from here, which we know is not very general and only applies to a certain number of data sets. So here we've seen today an example of how you can evaluate a mathematical theory by fitting equations to data. I think this is a good way to do it, this ensemble fitting, including looking at the residuals. And this is a little summary of what we've learned. That's step one. If you don't do that, it's not a problem. You'll just get wild fits, and then you'll have to go back to the drawing board and try to do that. You got to figure out how to implement the theory. What are the shared parameters? You've got to minimize the appropriate quantity to do the ensemble fit. Once you've done all of that, that's the process part, I guess, then you look at the results, and you have to look at the percent variance accounted for, and are the parameter estimates reasonable, and are the residuals random? And that can tell you whether or not a mathematical theory whether a set of data is consistent with a mathematical theory. And that's all I have to say today. Some homework for you. There are lots of concurrence. You'll have to find a concurrent schedule data set that reports response rates on each side of the concurrent schedule instead of just the ratios, or gives you the raw response counts. Find a set, test both the classic and modern theories, the way we've done it here today. Send me your answer, because they'll need to be graded. You'll need to be graded. For extra credit, this is for an A+, do that. That's really a different topic, but is it possible to detect? What if we do look at the residuals when we're fitting the single alternative hyperbola we all know and love to regular VI data? Can we detect any pattern in the residuals? That'd be an A+ for you. And it's due August 31st. And then I'll send you a composite report on your group homework. Okay, that's it.
I want to apply something like that only if I have a good account. So let's say that I found that both of these theories accounted for a lot of variance and had non-random residuals. In a case like that, I want to make a choice between these two theories, in which case I want to do something like the Kaike to see if I benefited from the additional parameters. I want to assert that because I have found that in the first case, the residuals are not random. That theory is false, and I don't need to go any further with that. And so when I'm looking at this theory, it's for these data, it's consistent with these data, and so I don't have any other model to compare. That's the way I look at that.
Suppose you could use parameters still.
Yes. In a case like that, for example, if you tried to fit it with a single exponent instead of 3 exponents, there would be an opportunity to use a Kaike. And in fact, if you do that, you find that Kaike favors the 1 exponent because it accounts for essentially the same variance and has random residuals.
I can't help but ask about this. With the Kaike criteria, you have to fit the model using maximum likelihood estimation rather than maximum variance, which means that basically the model has to be formulated as a probability density I don't know. I guess I'm just sort of asking, how would one go about doing that? You probably have to assume that the variance, you have to assume normal distribution at every value.
Yeah,
Could you repeat the question?
Okay. Well, I was just basically asking whether it's possible to use the, whether it's possible to formulate Hertzstein's hyperbola as a likelihood function, use maximum likelihood estimations. That's what you're supposed to use with Kaike.
Yeah, well, I'll tell you that I have no idea how you would do that. And I have problems understanding a Kaike, and consequently I have difficulty. I really don't like to use something unless I really understand it. And when I look at, if you know about a Kaike, actually I have found a reference that somebody recommended for me to help me understand that, but it's based on information theory and the idea of a model being close to the truth, and it's a very complicated kind of analysis, and I've never been in favor of just applying something because it's out there and people use it. So the truth is that I don't really understand a Kaike, and so I'd have to figure that out really before I decided how I might apply that to something like this. Yeah. But those things are very interesting and very popular, of course, the Kaike, and there are other things. There are F-tests that compare models. Those things are very interesting and very important, but where they really apply is in the inductive end of things, when I'm looking for an equation that describes a set of data, when I'm trying to find